So today, it's a long day. So we will make 2 lectures, one after another. So in the recording, it will be just one. So just continues. So today we're talking about group theory approach. So what is the idea of this group theory approach is we will try to answer several questions that you may have had during the lectures. For example, we consider different type of systems, like a shell model, Navier-Stokes equation, and different models. And for all of them, we had kind of the recipe how to rescale the system. We were obtaining the new symmetries, and it worked. So the question why it worked. First of all, why it works. Second, you may notice that it's not exactly the same recipe all the time. So it was, for example, for Navier-Stokes, it was slightly different. So why there is a difference, and still it works. And then also there were questions, for example, about ambiguity. So there was a different formulas for example, for the velocity amplitude, and it still worked for different formulas. So again, question why this ambiguity? There's many questions which you can answer why this works in principle, while they are, in every case they were answered explicitly, because in every system you can just do derivation and it will work. So, but the question what is the general features of all of this system, which and of the process that we do, that kind of unify all this as something on somewhat more higher the abstract level. So this is what we do. So we'll be talking about groups. So I think that everybody knows what is groups. I'll just recall the definition just to make a smooth start. So the group G is a set with a binary operation. So you can take 2 elements and create third element. No? So it's a mapping from G squared to G, such that 3 properties are satisfied. So the first property is that if you take the operation between any 2 elements of the group and then with the third element, it's the same as taking first operation with the second 2 elements and then with the first. So this is associativity. Associative. So the operation is associative. The second part is a neutral element. So there exists element of the group such that if you take operation with any element from any side, you get the same element. So this is for any A. So this is called neutral element. So it doesn't make any change. And then C is called inverse element. So inverse element means that for any element of the group, there exists another element of the group which we called A minus 1, which is inverse. So inverse means that you can take operation between A and N minus 1 in any sequence, and you get neutral element. So this is inverse elements. So that's it. So now we want to set up the group which correspond to the symmetries of our system. So what we will do is we consider we consider symmetries of Euler equations. Yeah. Remember having in mind inertial interval. So remember, our central goal is intermittency. Intermittency is what happens in inertial interval. Inertial interval is the intervals of scales where you don't feel neither forcing no viscosity, and in that case, this interval of scales is you can say that the dynamics is given by Euler equations. So I just recall you what the Euler equations are. So we consider incompressible Euler equations. Yeah. Okay, so we have different symmetries. So first, we list the symmetries in a way as we usually quote them, and then we will try to see where is the group structure. So usually what you say, that let U RT be a solution of Euler equations, and then you can construct new solutions. So new solutions can be constructed through different operations. So one operation is, for example, time and space translations. So when you do time and space translations, you just change or add the constant to coordinates, add the constant to time. So this is something easy. So new solution will be R plus R0, T plus T0. And this is, let's put prime now. So R prime is any vector, T prime is any number. Okay, the next would be rotation. So rotation, if you remember what you do with rotation, so rotation you do with, you introduce using the orthogonal matrix. So essentially the new field will be Q minus 1, U, QRT. So here Q is a matrix which is element, is orthogonal matrix. So it's a from orthogonal group. So this is how you do rotation, and then there is a Galilean transformation. Galilean transform. So what it is, you go to a new reference frame, which means that you add the moving coordinate Vt, T, and then subtract V. Right? So that's velocity in moving frame. So that's for any V in R3. And this all elements, it's what's usually called Galilean group. So you can, a Galilean group is obtained by making all combinations of these transformations. And then there is another group which is scaling group. So it has time scaling. And we, before we were always putting them together, so now we split them. So time scaling, what you do for time scaling, so you don't touch coordinate, but you rescale time by any number, and then you should divide by this number. So this is a rescale time field. A is positive number. And also we have space scaling. Space scaling is something similar, so you slightly different. But so you rescale just coordinate and multiply by the same number. Yeah, correct. So B positive. So this is scaling group. Scaling group. So how you remember? So how you would remember our previous space-time scaling is essentially what you do. So you take A equal lambda 1 minus h, B equal lambda, and then put them together, and then you get what we had. So what we had was this transformation that we used to write in this form. So for example, you see this lambda h will be because you multiply by b, divide by a. So it's lambda divided by lambda 1 minus h, so it gives a lambda h, right, and so on. So this is just to show you that the space-time scaling we used before, it's just combination of separately time scaling, separately time space scaling. Okay, good. So in some sense, it's good and bad. It's bad because here every group element is a transformation. So transformation at the same time, it's a transformation in the space of solutions. So in order to get new solution, you have to start with solution. And this is not a kind of a good space. So it's not good to work on space of solutions because we a priori don't have this space. So the way to proceed is how it's done in particular in dynamical system. You split the time dependence. So kind of you put time dependence into the extra operator, the flow. So let's just do it. So we first define phase space. Phase space. We call it X of velocity field. So velocity field which do not depend on time. So if you fix time, then now there is no restriction. So at any time, the velocity field can be whatever. So x is now velocity field. So any element x. Oh, let's write it. Space x capital of velocity. So x is the whole function. So x is our field. So now the next step, you define flow operator. The flow operator is exactly what gives you time shift. So knowing this, so flow operator is a map from x to x, parameterized by time. So this flow operator defines dynamics. So in which form? So x at time t is simply flow operator applied to x at time z. So if you have initial condition, then applying this flow operator, you'll give you vector field at forward times. So that's so what means flow operator? Usually it has well, most of the things I'm talking can be put in a rigorous form. So essentially, I will not write it, but essentially we always need that x is measurable space and all functions will be measurable. So what means flow is that flow at 0 time it's trivial. And another property of flow is that if you take it at two different times, it's flow at some of these times, right? So this is a standard definition of what means flow. So if you make one time shift, another time shift is the same as a flow. And so. Okay. Here, good observation is that usually phi t is defined for only for positive time. No? So it's semigroup. That's not very much important for us, so we will just think that it's a group. But usually flow is a semigroup. And in fact, existence of the flow is something very natural from point of view dynamical system, but it's very non-trivial thing from point of view of turbulence, because even if it's Navier-Stokes, we don't know existence uniqueness. But in principle, you can make tricks. For example, you can think that we consider the flow as a Navier-Stokes operator, for example, truncated at small scales. Then you have uniqueness existence, and then you say that you consider large Reynolds numbers and consider everything in dynamics in inertial range, and then you come to Euler. So you can make sense of everything, at least in the asymptotic way. Of course, without proofs, but it makes sense. Okay, so now we don't need time, because time is treated by flow operator. So as time is treated by flow operator, we can express all these transformations only applied to initial velocity field. So you don't need to apply it to every time. You just need to apply it to initial time, and then if you need further times, you apply with the flow operator. So we define symmetry transformations as maps, just measurable maps from x to x. So no time. And then I will just make the whole list of all these transformations in the same way as we did here. But so what I said that we know the flow operator gives us possibility just to go to any time. So all what we need to know is how the field is transformed at the initial time. So there will be, and now we write all these operators. So spaced. So time translation we don't need, because flow operator is a time translation. So the space translation, and we call it S, and remember it depends on a parameter R prime. So it maps U to U R plus R prime. So that's this transformation without time. So this is R prime is R free. Then rotation. It depends on a matrix. So it maps U of R to Q minus 1 U Q R. Then Galilean transform. G Galilean depends on V. So it maps U at R. So here it's quite easy, because when you put time to be 0, nothing changes here, so you just subtract V. Then time scaling. time scaling with parameter A. So it maps U at R, U at R to. So there is no time. There is no time. So you just divide by A. And finally, space scaling. Parameterized by B. Okay. So now it's already something better because we now have a set of operators. A set of operators which act on reasonable space. So every operator is a function from a phase space to phase space. For fluid dynamics, it would be from a space of flows to space of flows. So we can form a group. So the full group is generated by all of these operators. So by flow, and then just let's list them all. So this is a good sentence, but it doesn't make sense so far. Because in order to make sense, because so far you just, so in order for it to make sense, we have to understand essentially well, all of these operations, they make full sense because they define explicitly. The only complicated operator is a flow. So the information about flow that we need to add is how the flow commute with all the others. Yeah? Because otherwise you don't have a meaningful definition for the group. So we need commutation relation. So we need commutation relations. We need commutation relations. For the flow. So between the flow and the other elements. So if we give a commutation relation for the flow with other elements, the group will be fully defined. And how you find commutation relation, I just give an example. Commutation relation. Commutation relation you postulate coming just looking at this list of transformations. So, for example, let us see what happens if you take a composition of the flow operator and the time scaling operator. So time scaling operator, what it does, so time scaling operator is just U of R divided by A, right? So it gives you U of R at time 0 divided by A. So if this is a, and this coincides with what? It coincides with the initial condition of this function, right? So at time t, it will be this function. Right? So at time t, after you apply the flow, it must be U R t over A over A. So it should be this, because initial condition coincides, so the future time should coincide. Okay, so let's now do the same, but in opposite sequence. So I'm claiming that if you do it in opposite order, so you have to put here which one? T over A. So let's check that this is equality. So first you just put forward your solution. right, on shorter time. And this just divide by A. So you see it's the same. Right? So this is how you derive commutation relation for the flow.
So Alexei, you are just rewriting those symmetries in the language of flows.
Well, I want to, you see, the question is that these are all transformations applied to solutions. I don't want to work in space of solutions. I want to work in space of, well, in space which I understand well. So I work in the space of arbitrary velocity field at fixed time. So now addition of time variable is done through the flow operator. All other transformations, they are just made you can think of them as applied at the initial condition. And now you can just, now you have to, what is missing is how they commute. And how they commute, now you go back to this list and see what is the right commutation relations to define a group. Okay, so essentially, etc. So I will. I probably show the picture. Let's try to see the. Actually, good to see the table. In abstract form, at the moment you define all the commutation relations, you define the group. You don't need actually any other information. And let's see what group we define. And group is not very complicated, but it's complicated enough for all of our phenomena. Just let me. Yes?
It's T over A on the left and just T.
You see, T is a number. It's not a function. T is fixed number, A is fixed number. So what you do here, this is just U of R considered as initial condition. Then we know that if this is initial condition, then this should be a solution. So I know that the right way how the flow should apply, it should give me this.
So it's T over A.
And here T over A. Here T over A. So look what you do. You when you apply it to the initial condition, this is what you okay. This is that, and here it will be U of R T over A. This is what you mean. So this just moves you to the new time. And this operator just divided by A.
S does not scale the time.
On the left, why is not T over A in the index of phi?
Why is not T over A?
Here?
No.
Here?
Yes.
Because you see, so if you give me initial condition, which will be this, the moving to time t will be that. So see, if you give me this initial condition, and I evolve it at time t, I'll get this stuff. Well, heuristically, because you see it 8 times slower So, so
You're considering solutions, not fields, not arbitrary fields.
so this is U prime of R. So what is phi t of U prime of R? It's U prime of RT. And U prime of RT is what I've written here. This is solution. Yeah, that's simple but funny.
But then they don't commute, right?
Then they don't commute. That's the point. That's the point. They think that they commute, but they don't. So now this is a full table. So what you can see is in the table that there is just one. So what is this? So you take this operator composed with this, and this is what this is in this version. So all of them are almost commuting, almost quasi-commute in the sense that the one by the other is equal to the opposite sequence, but probably with different parameters. Yeah? So it's kind of quasi-commute. So most of them just commute, part of them just quasi-commute, and only flow with Galilean transform, it absorbs one more operator, which is shift. Because if you first change the coordinate system to another speed, and then evolve, or do it in opposite directions, your system will be equal, but shifted. So you take a shift. So what is important that this is not trivial set of computational relations, but at the same time, first of all, it tells you that the structure of group is rather simple, because what you can do always, you can just always change an order in any composition of operators. You can always order them. Yeah? So it means that the general element of the group is just ordered product of all of them. It gives you any element of the group. And what also we see is
it's not clear with Galilean.
It's clear with Galilean because the shift you can move easily, because shift quasi-commutes with everything. So you can always order. So that you can check. So the group structure is simple, but there are two things. So there are two things is that so what is most important is the commutation between the flow and other symmetry transformations. So they all commute, but except for the two of them. So one which does not commute, I showed. So that flow does not commute with time scaling. Almost commute. You just need to change time. And it does not commute with Galilean transform. So kind of it almost commute, but you don't change parameters, but you add one more term. So there is a two non-commuting relations. So we will actually, and this is these two relations is the core of the whole series that we were studying for the last 7 lectures. Yeah. Say that, okay. Sorry. Phi because if you put here t, it will be at here. Okay. Hmm? Well, it's a table. So in one corner there is this relation, in another corner is opposite relation. The equal is just up to redefinition of t. It doesn't turn on. The other relation is just it's starting. No. So phi by this T of A. And another phi of A is AT. It's just the same relation up to the definition of T. Well, I'll write it. Put it opposite way. STS A phi T. It equals to this, but and this is exactly this. You just change T. Okay.
What is group characterization of this group? So it's finitely generated group by 6 elements, yes? Is it big group, small group? It seems that it's
Well, this is Lie group of dimension that you just compute how many parameters you have.
it's solvable, I guess.
Well, solvable. I don't. I'm not sure. I know what it is, what it means.
So that's, if you consider commutant of the group itself, yes, you will have a smaller group.
Okay. I think so. Well, probably.
I'm not sure about the year.
Well, that's a good question. Certainly, this is very Galilean group is very well known, so we can check, and then what edit we add scaling group. Scaling group is rather well behaved. Well, that's a good question. So anyway, we we will not use on the lecture these properties. But at the very end, I will mention these kind of things. So that's a good moment. Okay, so now let's remember what means symmetry. Yeah, velocity fields in space, not in time. Huh? Infinite dimension, yes. No, but it's a representation. Group property doesn't care about representation. Yeah, it's represented by transformations, but group is group. Yeah. Okay, so what we do is we move by using that abstract formulation. Formulation. So from now on, we forget that we're actually dealing with fields, velocity fields, and so on. We just have a group. It's defined on certain phase space. It certainly have to be infinite dimensional, and all we have is in commutation relations. And the second fact that we use is that group elements are represented by maps. Actually, this is automatically 1 by 1, 1 to 1. To 1, measurable maps. So that's, from now on, this is only what we assume. So we forget that we started from Navier-Stokes, for Euler, for whatever. Okay, so now let's revisit a little what means symmetry. So what means symmetry? Symmetry in the usual sense. Symmetry in usual sense means that having solution, right? And having the symmetry operator S, what you can do, the operator S applied to every point maps you in another solution, which is also solution, right? So this is S. And the fact is the solution means that this is defined by the flow from the initial condition. So now this is kind of diagram that you have to commute. So what it means? So it means, for example, let's compute this in this direction or in this direction. So what it means is that in this way, you first apply flow, and then S. And in this way, you first apply S and then flow. So in usual sense, symmetry means that flow operate commutes with symmetry operate commutes with flow. So commutativity. So so usually the transformation is a symmetry in that sense if it commutes with the flow. And we already see that there are two symmetries which do not.
Both hand side are the same.
Hmm?
Both hand sides are the same. Three.
Okay.
Right hand side. It doesn't commute this.
Ah, okay. It's first S. Yeah. This is, when you dynamical system, people you learn to write from right to left, right? But if so you apply it and then you write from right to left. Okay, so immediate observation is that time scaling and Galilean transformation do not commute. With C. So they're not quite symmetries. Right? They're not quite symmetries. So in the case of time scaling, you also need to massage time. In the case of Galilean, you also need, you need to shift. So they're not quite symmetries. But this we can, and this is true. So this at the same time, this we can treat if we now remember that our goal is not just a symmetry. Our goal is actually statistical symmetry. So we are about looking at the symmetry of statistics. So let's define what means statistical symmetry. So we are interested in definition. I write it here. So we will be defining statistical symmetry. From now on, the symmetry will always mean statistical symmetry. And for that, we need a branch of definition. So first definition is about invariant measure. So a probability measure mu on our space is called invariant if, well, this is standard, if it does not change under the flow, yeah, for any time. So it means that if you have certain statistics at certain moment, it's the same at any other moment. So you evolve the system, but statistics does not change. So this is probability measure, and this is with what we was working all the time before. So the second is the transformation is called statistical symmetry. And we will I will not always say statistical, but you always remember this statistic, that is any symmetry we are interested in statistical. If the measure so if you take an image of the measure of push forward the measure by this map, it will be invariant. It will remain invariant. Invariant if mu is invariant. So if you take invariant measure, it maps invariant measure to invariant measure. So that's exactly extension of this of this definition, which we can. I think we can. So if mu is invariant measure, then this is invariant measure. Definition. Well, measure is in X. X is measurable space. For Navier-Stokes, it's space of vector fields. Which vector fields I don't want to specify, but in the infinite dimensional space. Anyway, the whole theory, I think, doesn't make any non-trivial sense in finite dimensional spaces. So everything, all not interesting conclusions that we're getting, I never could make an example of finite dimensional space where everything works. Works non-trivially, in sense of giving something interesting. Okay, and then, so now you have to remember about this difference. So this means this is symmetry over the dynamics. So giving measure, invariant measure, it gives invariant measure. So now there is another concept is the symmetry of the measure itself. And this is usually, always happens in dynamic system, and this usually gives a no in the brain, but you need to know how to how to distinguish. So statistical symmetry S is restored in a given measure in mu, in invariant measure mu, if S mu equal mu. You see the difference. So it's statistical symmetry if it maps invariant measure to invariant measure, but maybe different one. And mu is symmetric if it is mapped to itself. Otherwise, it's broken. If the fixed point of the group action. Thank you. Otherwise, symmetry is called broken. So I think we are done with definitions, and now we can check something. For example, we can check that all symmetries, all operators that we have in a list, except Galilean. With Galilean, we will see how to treat it later. But if you forget about Galilean, that all of these operators, they are statistical symmetries. And let's just prove it. Are statistical symmetries. So let's just make a proof for. Let's make a proof for time scaling. The most controversial. So time scaling is not a symmetry, but let's show that it's statistical symmetry. So what essentially we have to do? So let us assume that we have a measure which is invariant, and let us show that this is invariant. So what is it means that we have to show that we have to push forward it by the flow. So this is time scaling, right? So this is S time scaling A mu. Now we can put them together. This can be flipped. But remember, T over A. And then we split it again. But mu is invariant measure, so this is mu. That's it. So we found that this measure pushed forward by the flow is itself. So that's it. So so now it's already better. So at least we save time scaling, and for time being we will not care about Gaussian transform. And so far everything, at least except the Gaussian transform, everything is a symmetry, statistical symmetry. Well, at least one invariant probability measure. Well, that's of course nobody. Well, first of all, unfortunately for the turbulence, the question is much more. Problems start much earlier. You have to define what is flow. Yeah, and you can define the flow in a reasonable way, in fact, but then you have to define, like as I said, the truncated Navier-Stokes. But then the whole theory only applies asymptotically in the inertial interval, and this also have to be defined properly. Yeah. For example, for the solvable system, we know everything.
But for the truncated Navier-Stokes, do you know that there's at least one?
For truncated Navier-Stokes, if there is invariant measure, I think so. I'm not sure. Well, truncated Navier-Stokes is a finite dimensional dynamical system. Space is not compact. Yeah. Space is not compact. That might be, but you can consider periodic. Probably you can consider periodic solutions, and then you're in a compact space. But periodic solutions, no, it's not. It doesn't help because it's physical space. It's not phase space. Yeah, actually, I cannot say if it's available or not. Yeah. So anyway, truncated Navier-Stokes is finite dimensional dynamical system. On Rn, where n is very large, is number of degrees. That's a good point. Yeah, no. I think that for truncated there is a uniqueness existence of initial conditions, and solutions do not go into infinity because you usually truncate conserving energy. So you conserve. Solutions are bounded. So norm is bounded. So then you can prove probably. Yeah? Mm-hmm. Okay, so let's make a short break and then we continue. Short break, like until 4. So now we go to the something real. Oops. So let us check how we can derive a hidden scaling symmetry. So we start with the setting. So we don't need a full group. So we will actually only need 3 elements of the group. And I will give them different names. So H will be a time scaling group. So H will be consist of element HA, which is time scaling with parameter a. I just give a shorter notation. HA will means time scaling with constant a. So this is time scaling subgroup. Then we take G. G which will be, I don't give names because we will not even need this notation. So G will be the subgroup of spatial scalings, the space scaling subgroup. And then the full group that we will take, the symmetry group that we consider, so I called S, and it will be just direct sum of the flows plus space translation plus and time translation. So we consider a group which consists of flow, space, time translation, and that's it. So important thing is so take the commutation relations. Commutation relations, first of all, the space translation commutes with everything. So for any G, for any space translation, we have the G phi t equal phi t G. Well, for any G and any HA of H, we have, so the flow commutes with G, with space scaling. Space scaling commutes with time scaling. Oops. And now we remember that we have non-commuting relations between time scaling and flow. And non-commutation is changing parameter. So that's essentially everything we will need from now on. So these three relations where the important is that these two do not commute. No, all the rest you forget so far. All the rest you forget. We will, I hope we come back to it closer to the night, but at the moment, at a certain moment we'll understand why we need Galilean invariance. Okay, so now let's remember. So what we're addressing the problem of intermittency, problem of explaining intermittency. Or phenomenon of intermittency. Essentially, in group language, what you can say is that all space-time scaling symmetries are broken. That's exactly what intermittency means, that all space-time scaling, that all combinations space-time scaling are broken. Are broken for the invariant measure that we have in our system. So we have invariant measure in our system, our statistics, all of them are broken. So that's a measure is not itself. It's also invariant measure, but not itself. So and we want to understand this situation by so they're all broken, but there is this multifractal theory, which is phenomenological. So it tells you that all of them, but each of the symmetries is restored on a fractal subset. Let's say of X. So what it means is a complete mystery, in fact. Yeah. So instead of formalizing this, what we do is essentially, so as I said, depending on HA. So for each different HA, it's a different fractal subset where the symmetry is restored. So how you would treat this this idea? You can treat by the idea. So the problem is HA. Yeah? So problem is HA because kind of for every different HA, it's kind of restored in a very funny way in certain subset. So the idea is to remove HA. Yeah? So construct a symmetry by fusing HAs. Just collapse. If all HAs, well, certain project collapse collapse on the same transformation, we don't have we don't distinguish different HAs, and then we have a hope to recover this image. So this idea, but now we will make it exact.
Can you say more? What does it mean to be restored?
Restored, it means that we will make a new symmetry.
No, fractal subset of X.
That's a good question. I cannot say you what it is. Idea is that in turbulence, idea has to do with velocity differences. So the idea is that velocity difference scale in the right way on a certain fractal with certain Holder exponent. With a different Holder exponent, they scale on different fractal. So usually this is an idea. This is more or less what Simon was explaining. This is certainly not an and actually this is quite established concept in for example, for the fractals and from Mandelbrot ideas and so on. Okay, so what means fuse H's? So H's are all elements of the subgroup, and in a group theory we have a concept what means fuse its quotient. So we take equivalence relation. So we make equivalence relation telling that we don't distinguish between different H, simply. So so let's first work with so it means that quotient. So first, we need to have two quotients. One quotient will be of phase space, another quotient of the group. Two different things. So first, let's define what they are. So phase space, X. So we say that 2 points in the space are equivalent if they can be related by element of H, group H, for E positive. Yeah. So two elements are equivalent if they can be connected by time scaling. And this is equivalence relations. So you have equivalence classes. So you define equivalence class. So we have a nice notation. H capital is a subgroup of X is just all X primes. So equivalence class. All velocity fields which can be obtained from this one by time scaling. And we say that this is a class. And then you define quotient space. It's called H, or X divided by H is a space where the point now is not a point but the class. So that's okay. The next point, so with the space it's easy. The problem appears when you start to do it with a group. No, X is not R3. X is a space of fields on R3. It's a space of fields in R3. It's infinite dimensional space. Yeah. 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 Or for the shell model, which we'll also consider, X is a space of infinite sequences. Yeah. So it's C infinity. Okay, so now let's do the same with a group. So the symmetry group. So we have this S, which is what we said, all of that. Sum, and what we want to quotient it with respect to H. So again, we remember what everything means. So essentially you want to carry the equivalence relations also to the images of two different. So you take two different the same point and two different maps from S, and you want to by saying that they should be equivalent, you should define equivalence relation between the maps themselves. And here, what you see that C prime, it should be what it is. It's C and X and and equivalence means that this equal to that with certain rescaling, right? So let's say this equivalence to this, and then you can think it in two different ways. So that S prime of X equal SHA of X. This is one of the way to write this, and another way is the way around. Is that S prime of X equal what do I write? No. Okay, let's not make a derivation. Let's make it to definition, and then we'll see that it works. So there is definition of the cosets. So there is a left coset of S, which is called S. For each S, you can define left coset as a set of the products of the compositions. And you can write right coset. So now, so cosets is essentially, you see that everything is defined up to time scaling, so it's meaningful to put HA from one side or the other. So important situation is when they are equal. So the definition is that H is called normal. Normal if SH equal HS for all. Yes. It doesn't matter which side you compose. It's the same thing, and in this case, there is a group. There exists a quotient group. Which is called SH, and it's a group of cosets. Doesn't matter in which sequence I write. And why it is a group? Because this group, if you take two of them, you can define the operation as in this form. And what your exercise is, it's only consistent under this condition. Essentially, because take any member of this set, and you have to be able to switch them without losing the set. So that's kind of very basic thing from group theory. So you can create a quotient group, which means that quotient group which will kind of which will not distinguish among its members which correspond to H, only if the H is normal. And that would already solve the problem, but unfortunately H is not normal. So that's the point. H is not normal. Problem. H is generally not normal. So how you see it? You just so this should be for any element or from a group, and you take flow. So then left coset is AH, T, and right coset HA phi T, which is, so here T is fixed, right? And this, remember that this is what? This is phi AT HA. So you see that's generally different from that. For general flow, these are different things. So generally, H is not normal, so you cannot make a quotient. So what we want to say that we will go the other way. Flow is normal. Yeah, but flow is normal. But we don't want quotient with respect to flow, which is, by the way, also people do in dynamic system. Right? But we don't want to remove flow. We want to remove scaling, time scaling. So what do you do? So now, if it would be general, not subgroup which is not normal, it would be hopeless. But fortunately, it's not just arbitrary not normal group. It's not normal group with very specific commutation relations. We will use this commutation relation to do something which will make actually quotient. Not exactly quotient as we used to it, but something very, very similar. So what we do, let's remember about, let's recall the structure of space X. So what means structure of space X? So let's take point X, and let's consider the equivalence class, and we have a solution. So at time t, it brings us to that point. So this is a solution. We can take another point from the same equivalence class and consider different solution. Now, remember the equivalence relation. So if you go at the same time, you will be somewhere here. But you come on the same equivalence class if you go at a different time, and different time is exactly AT. That's our commutation relation. So actually, you respect the equivalence relation if you adjust time. And this can be done at every point. So what we will do, we will synchronize time. So you need to synchronize time. If you want to synchronize time, you need a reference. So you synchronize your watch with respect to something. There is no a priori any something here, so we define this something. So what we do, we define a representative for each equivalence class. We put a representative. We just define one point, and then it gives you certain subset Y, which we define. So define definition. So Y, which is subset of X, is a representative set. If for any point you find unique representative Y, so there is unique transformation, unique A depending on X, positive, such that Y, which is HA of X, belongs to Y. Essentially, so what it means that, and then we say, we also define that the function A, which is from X to R plus, is measurable. So the function which tells you, give me any point, it puts you to the one representative. This will go to the same representative. So for each class, you get a representative. So now what you do, you now for any solution you adjust your watch, which corresponds to the projection of all these curves on this set. So we define certain time which flow according to the choice of this set, and adjust the watch of every solution according with the time. So how to do it? That's actually easy.
Is this related to the quasi-Lagrangian frame?
Not yet. Galilean will give a Lagrangian frame in the same way, but this is not.
Sorry, we can see X measure.
Well, X is a set. X is a space. X is a space. Y is a subspace. And what we say that for each point in the space, we choose one representative point on each equivalent class. We choose one representative point.
Yes, but if we claim that A is a measurable map, then X should also have a measure.
No, X is measurable set.
Measurable.
Measurable set. Yeah, I think I said it from the beginning.
There is a predefined measure.
Well, there is a predefined measure because this is a measure with which we work. So we always assume that there is invariant measure, which this is a probability measure, which is invariant measure, and we want to study its properties. We assume that all the symmetries are broken for this measure, and we try to restore this business. So that's why measurability, the measurability is the only thing we need, because we need to be able to work with the measure, and luckily, dynamical systems theory allows to do all these operations. So what you do? So somehow what we will do, we synchronize all the watches everywhere. And if we synchronize all the watches, we kind of recover this structure, and then we just collapse it to Y. So this gives you actually dynamical system on representative set. So let's just construct it. So construction of flow on Y. So first is, as I said, change of time. Remember the change of time, we know that we need the change of time corresponds to A. You see, if you go to another trajectory, the change of time is controlled by A. A is at each point is controlled by this function. So we have the sensible way how to change time. So let's just do it. So we define time tau as A dt. And then A, we take this function, A of x of t dt. At every point, x of t is a solution. So it's A phi t x dt. So we defined change of time at every point differently. So this gives you any point x you are, I know, change your watch by that amount. That's a rule. Whenever you change the watch at this amount at every point, you change a measure, right? Because measure is invariant measure. It has to do with time, and we know how the measure is changed. This is you take textbook from dynamical system, like Sinai's book, and the corresponding invariant measure is changed by, it's mu A dx. It will be A of x divided by integral dx. So this is just a prefect. So that's a rule how to change a measure. And finally, we define projector. So y equal p of x by definition is so what we did. So this is just projector. This given point x. P projector is given any point x. It just projects you on y. Yeah, and then we have other things. So I understand it's already hard to follow, so I give directly the result. So if we construct the map out of this, essentially the map will be exactly like this. The map psi tau of y, which is defined by projection of the original flow of y, and tau is related with the time by this formula. So this map is a flow on y. So essentially what I'm telling is that we don't have commutation, but the structure of the dynamics is not actually very random. The only difference between trajectories is a different time dilation. So what it tells you is that you actually can project all the dynamics to the subset respecting dynamics. So you project, and you will get dynamics on y. So you get dynamics on y. And this is directly our flow. Actually, this is exactly a rescaled system. We will see this is exactly a rescaled system. So the second point is not only we project dynamics, but we can project measure. So we had a measure on a full space, mu. So we can cleverly project it on y, and it will be invariant measure for the new flow. So essentially, we want to reduce both dynamics and statistics just on y. And this measure is also, this is exactly just projection of this. So the second is that the measure which is a projection of this mu a is invariant for this new flow.
You need y to be invariant set.
Yeah. No, y is not invariant set. Y is any set. The only property of y is it should contain just one point at every equivalence at every. It's not invariant set. It's just actually it would not be possible in application to have it as invariant set. That's the point. So it's not invariant, but still I can project the whole dynamic.
But then there is a dynamical, issue, yes, there. For instance, you might have on set this y of tau could be, say, periodic, while the original system doesn't have periodic.
No, if you have periodic trajectory, you may have periodic trajectory, and x will not be periodic.
Yes, and x will not be periodic.
Yeah, that's possible. Yeah.
And this okay.
This is okay. Actually, this is not only okay, but this more or less the idea.
Okay.
Yeah. So you take something which is badly behaved. Yeah, you take something which is probably badly behaved, but after you project it, started to look nice. Okay. Okay, so that's we are coming to the.
Another question. So there is a special point 0, which is quite different from other points because it doesn't have a line. It is just one point. Because of this, we ignore it. Yes,
No, I don't think we have to ignore it. No, okay. You're right. And you see it quite. You're right. 0 we ignore because you see it on on the scaling procedures. It's the only point for actually where if for the 0 field you cannot define positive amplitude, and we always divide by amplitude. So you're right. So there. So that's essentially this is a property. A of x should be positive, and this actually implies that there is no 0 field. But that's okay. From point of view of application, it doesn't make a I don't see any.
potentially you can make have x, ha of x, ha of x, and so on, which would converge to 0. Yes, so this, but 0 kind of means 3. So this would not be.
Well, it doesn't seem that we don't really need the structure in X. We just need that it's measurable. So
So you never use topology.
no.
Only
Well, we don't use, for example, linear structure. 0 means linear structure. So we don't use linear structure.
no, topological structure.
Topological structure we use because we're talking about measures.
No,
But-
measure is measurable. Like as a dynamical person, there is two very different laws, which is based on topology and which is based on measure theory. This is it's not the same.
Well, we're talking about that X is a measurable set. It means that measurable set.
Topological structure. No topological structure.
Well, there is sigma algebra and all this. This is, but I don't ask for anything else. Yeah, so I think we're good. Okay, so this is the first part. So first part we say that you can project dynamics on y. So the question now, what about symmetry group? Symmetry group, so remember that symmetry group was CT, G, H. So H we kind of project away, right? This goes to, this goes away. This goes to psi tau. So now whether we can make sense of space scaling. And remember what means, what essentially we need from this G. We need that G is a symmetry, statistical symmetry. So it maps invariant measures to invariant measures. So we should want to keep it. So that's second theorem. So this is not possible. But what is possible is let's take any element of J and new invariant measure of psi tau. So just the setting, the element and mu invariant measure of psi tau. So if you take just push forward of J applied to nu, it will not work because J is a map. It does not respect Y. It will just go out of Y. So what actually can be done is then we call J star, and now J star is an operator from space of measures to space of measures, so the space of probability measures to probability measure, such that to define as G star nu equal projector with J push forward. Since it's projector, it stays on Y. Nu, and then remember this operation, exactly this operation, but not with A, but with AJ. So this is a measure on Y. So the statement is that J star nu is invariant for psi tau. So what that means is that the corollary is G star is a statistical symmetry. So we do have statistical symmetry, but we cannot represent it as a map. We cannot represent it as a push forward by a map. It's something more complicated. It's an operator which maps already directly measures to measures. So now I will show you some more.
Not the same as you consider G element projection G.
No, there is this part, and this part is a change of measure by density multiplier, non-trivial decimal. This part is essentially what is important. So let's just write now diagram that we wrote many times. So we have measure mu. We can project it. Remember, the projector of measure mu is this, right? That's our projection from theorem 1. Theorem 1 projection gives us nu. Yeah? So this is measure on x, this is measure on y. Now, from nu, we can take theorem 2 and give us new measure, which will be on y and invariant. And we can now commute this diagram. So what we can do is from mu, we can go to mu prime by any space-time scaling with any a. And now on this level, we can apply theorem 1 and just project. So that's exactly diagrams we did before. And what you see that, so the theorem, all the theorems show that they commute. So the result will be the same if you go this way or that way. But that way depends on A. So you can make different ways. And so theorem tells that you always get to the same point is the same as going through G star. So the G star is our hidden scaling symmetry. So we did the fusion. So this way, we rescale. We make space-time rescaling with arbitrary time rescaling. At this time, and the result does not depend on time scale. So we did what we wanted. So just a couple of statements and then we relax. So definition is hidden scale invariance. So definition of scale invariance, we say that this hidden symmetry is restored if it does not change measure. Same business. And then finally thing is the final theorem is first thing is so the property of hidden scale invariance does not depend on the choice of representative set. Okay. Whatever representative set you do, if it's in one representative set, it's hidden scale invariant. All other representative sets give the same result. So essentially, yes.
Here, should there be mu instead of mu? Mu A J.
Which play?
In the definition of J star.
In the definition, this?
In the definition of the J star, should there be mu instead of mu? Because
No, new, because that's, you see. So what you do? So this is new. This is a measure on. This is measure on y. This is just adding a prefactor. Now you move it by j, so you move it outside y to x, but p put it back to y. So p is a projector. So there is two steps. So g goes out of y, but p goes back to y. So that's the formula is consistent. So given the measure on y, it gives you the measure on y.
okay, but what's the definition of mu A?
Nu A is just the same thing. So nu A is by definition, nu A is the same formula. So nu A j dy is this A G Y A G nu UI nu UI. It's what's in dynamical system is called the transformation corresponding with change of time. So so you take the measure, and then take the measure which is absolutely continuous with respect to itself, with this multiplying by this density. It's measurable function. So you multiply measurable function. So so this measure is absolutely continuous with respect to this, and this is exactly the transformation.
Theorem 3 tells that if you take some mu, and for one set y, the corresponding mu was
Thin scale invariant.
still invariant, then if you choose another y,
No, is a property remains.
It's property of pair mu and g.
Well, this property remains.
Yeah. So, so after you remove dependence on y,
You cannot remove dependence. At least you cannot define anything without setting y. You cannot make, at least I don't see any way how to make abstract definition without setting y. So you need to set y.
yes, but how you choose y, it's not important. So
It's not important. Choosing different y, it's all elements become different, but the equality remains.
yes, so but then it becomes property of mu.
Then it becomes property of mu. Exactly. Exactly. Then
But the question is property of just mu or pair mu and g.
it's a well. In fact, it's pair of mu and g, but g is fixed. G is because it's a pair of mu and g, of course. Yeah, of course, mu and g, but g is fixed. G is one that.
Pair mu and g is good.
Yeah.
If for some
Yeah.
y
Yeah.
it's true, but if
Exactly.
it's true for some y,
Yeah.
it's true
Yeah.
for
Yeah.
everybody.
Yeah. So that hidden symmetric version of g is restored in mu if this is true. That's very good point. So what we do now, we now kind of sure.
Yeah, what is A composition with J of Y? Because J, as far as I understand,
J is so J is x to x, right? And A is x to r plus.
yes, but Y is big.
Y is and then you integrate. No, J. You consider J limited to Y, no? No, because this is of Y. Function. This is a measurable function of Y integrated with the measure. Good.
If you does G star has if you take G1 and G2, then we'll have
That's well. I wanted to skip it, but this is so that's another property. Is that G star preserves group structure. So it means that if you take G1, well, if you put G star and then apply it to another G star of nu, right? So with one transformation, another transformation, it's the same as G prime. So actually, this is a good point. So, we not only keep the symmetry property, but we also keep the group property. So it's really a quotient. Only that it's not an original quotient because we are not anymore in the same representation. It's not anymore represented by maps. It's already just transformed. We kind of lifted our representation from maps to to maps from measures to measures. And on that level, we have essentially the group which is direct equivalent of quotient, but not exactly the quotient, because exact quotient doesn't exist. Are we good? So now we relax for some 20 minutes. There will be drinks, food, and then we resume. So this is the plan. The first plan is that I will briefly show that all we did is exactly what we were doing before for shell models, and almost exactly of what we were doing for Navier-Stokes. And Navier-Stokes had one more ingredient. And that ingredient, we have to understand what it is. It has to do with Galilean transformation. And after that, we finish. And at the end of the second lecture, I propose that we kind of can make discussion of what is not known, what is interesting to do, and so on. So it's a long break. Okay. So let's just do something concrete. Shell model. Shell model, so the space is our sequence, infinite sequence. And then, remember we had the operator which is scaling operator, which goes un goes to lambda un plus 1. So the space scaling corresponds to just changing index and then multiplying by lambda. And then HA, the time scaling, is it's always the same. It's just divided by this number. So space scaling and time scaling. And then we need to find we need to define the representative set. So one of the statements that you can, by the way, as an exercise prove. So remember, so there was a definition that representative set is y is a representative set if there is this function a of x, which satisfies these properties. So in fact, this function satisfies these properties if it, and only if it satisfies, where it is, if it satisfies that a HA of x equal a of x divided by a, and this is all positive for any a. So this is any function which satisfies this property works. So the function that we take in a shell model is, remember we had this E0, and what we took is a geometric series, or the series. So you can check that whenever you apply, essentially what you need is that whenever you divide u by a is also divided by a, and you can see that it's just a comes. So it satisfies this property. And we already was talking that this is not the only choice. You can take whatever function a, which is positive, and it's degree 1 positive homogeneous. No, that a was arbitrary. So now this is our definition of that a. So this is our definition of a from a Euclidean group. We take in a shell model, we take that a0 that we had before. It serves. This gives us a representative set. Alpha is just any number sufficiently small so it converges. What? This is like a norm. Yes, this is like a norm. You can take a norm. No, but you can take a norm provided that the norm is properly defined, so it converges. Yeah. Essentially, A can be A is well, it doesn't have to be a norm because we don't need triangle inequality. I think that's okay. So this is it. So now what we do? So now we have actually do two steps. First we want to first of all we want to move to the inside inertial range. So first move inside inertial range, which means that going to this reference frame. So let's, instead of x, we will consider x prime, where we rescaled everything to the inertial range. So this will be, by definition, m times this operator. So it will be lambda m, and then it will be n plus m. So u, and we call n capital plus m, n. So that's the first step. And then we define already this y on top of this x prime. So y is what? Is h a of x prime, x prime. So this is by definition our projector. Let's call it u capital N. So now what is this u capital N? U capital N is this term, yeah, divided by the, so it's lambda m u n plus m divided by a from the same thing. Lambda m cancels. This and this can be written. Remember, this we just defined that as a is am. So you just can check this. So same as we did before. So this transformation to rescaled variable. So this is rescaled variables. So this is our rescaled variable. Rescaled speed. So this is exactly rescaled field as we defined, rescaled speed as we defined. So what you can see is that projection on a representative set with this choice of A is exactly rescaling operation. That we did just manually before. So now I will not give. Yes.
Big M is the cutoff, right? You're cutting off the sequence. Big M is the cutoff, and then little m is like you're applying the dynamics of G. You're shifting it.
Well, what I'm telling that I don't want to consider the dynamics of x. I want to consider dynamics of x prime. This will be my variable, because I want to be inside the inertial range. So now I'm applying the projection for x prime.
But G is like you're shifting downwards.
Yeah, I'm shifting downwards before doing the rest.
So can you make it like a diagram? Because there's a shift.
Yeah, but, you see, G commutes with everything, so it's harmless. G is always commuting. G commutes with everything. Because this is how I make a connection with so in original shell model, N0 is centered at the forcing range, but I want a theory which is centered in the inertial range. So I first move my origin in scale here. and then I perform the whole process here.
G also shifts it even more. G, the function G is like a shift.
No, there's no G now. You see, G is a symmetry. So G commutes with the flow. So X prime has exactly the same flow as X. So I'm just consider flow on X primes. I'm consider.
G is not related to lambda. G is a lambda, beta.
Yeah, it's this. G is this.
It's like a shift.
It's shift.
Lambda.
Shift and lambda. Yeah, but lambda cancels.
So it's like you're shifting m times
Shifting m times, yes.
without lambda.
Without lambda. But if you the shift which preserves the flow is with lambda. All right. I will tell what it gives. Maybe it will be more clear. So this theorem that is written below, it tells you that u is a function of tau, our rescaled variables with respect to properly rescaled time satisfies the rescaled system. And the rescaled system is nothing else which is this definition of this flow. So a rescaled equation that was written for the shell model is exactly correspond to this flow. So this kind of guarantee that whenever you do this rescaling with arbitrary A, which is homogeneous, and then you take this u, then you take tau, you substitute, make derivations, and you get equation which is consistent. Yeah? So which will stay on this representative set. So essentially, the rescaled equations that we obtained is exactly this, correspond to this flow. So it's just this is what we did, in fact. And then, yes. G, no, you don't understand.
Because it's like you're forgetting this. It's like you're shifting the coordinates. You're looking at.
I want just before doing. So I had a dynamics CT on X. So what I want to do, I'm defining new dynamics, which is the same CT on X prime. It's just the same dynamics on X prime. And X prime, I define X prime from X by applying GM. So now I apply all the theorems on these dynamics X prime.
But GM is just shifting coordinates.
It's just shifting coordinates.
You're shifting.
Well, why I want to shift the coordinates? Because I want to obtain exactly the same equations that we had in the previous lectures. If you don't shift the coordinates, you also get the equations, but they will be shifted. All right. So it's up to. And then actually, I mean, you can go straight, and then you get a coordinate, and then you can recover the same coordinates after applying G star, GM star. But that's just a bit more complicated. I want to have the same equation. So I'm just going to new dynamics, which is the same. And this I project on a representative set. And it gives me exactly the same equation as we did before. Equation of motion are also the same. And then theorem 2 gives us G star is a transformation of measures of statistics measure statistics of U tau. Because remember, after you get a rescaled system, what we said, that there is a transformation which transforms both velocities and time, which does not change equation. What it means is for statistics it means this transformation. You change time and velocities. Yeah, and you get the same also invariant statistics. So that's exactly. So what I'm telling you that all the computations for shell models they fall into this directly into this formalism. Just give a hint of how would you proceed further on. What is structure function? Structure function, the way how we defined it, it was mean of am u in the power p. The average of the amplitude in the power p. So what you can what you can check is that it can be written as LMP integral a g m x p mu dx. So what this gives is that I can write exactly the structure function of shell model, but purely in terms of group of group expression. So essentially, you can define direct analog of structure functions, but purely on the language of our group. And then you can make the same steps. So you can connect this to certain integrals of certain measures. Mu m dx. Okay. Essentially, from this on, I certainly will not do it now. But in the same way it was done here, you can make the same kind of line of arguments by defining the first defining the iterative relation. And then from this deduce Perron-Frobenius mode. And from this you deduce scaling law with generally anomalous exponent. So on this level, on the group level, you can do the same. So if you're interested, you can get inside the paper and see how you define. So what is important? So if in case of shell model, we did really just analytical transformation on the functions. So here, all what you use are commutation relations. So essentially, you do exactly the same, but it turns out that all operations we needed for shell models on a group level are provided by commutation relations. So somehow the scaling laws are determined, well, existence of scaling laws originate from commutation relations. That's a message. Okay, that's it for shell model. Now let's try to see what we do for Navier-Stokes. And that's interesting. Navier-Stokes. So what Simon did last time. So here our point is the field. The field where R is up. Our point is we have infinite dimensional space. Our point in the phase space is the whole field. Then we have a scaling operator. It moves field to lambda u r over lambda. And then we have the time scaling operator, which moves ur to ur divided by a. So what is a? It was defined. This was defined as a positive first degree homogeneous functional. Example is that you take average on a sphere. So that's our function which defines our representative set Y. No, there it's exactly. So now let's come to it. So, however, what was, changing radius is not actually important, because changing radius means that, again, so you can just from U to go to just different, rescale it, and then work with, do all this procedure already on this field. No, no, the Euler. No, we're talking about Euler. Sorry. So, however, what Simon was defining was not exactly that. So, what he was defining, he was using such a funny quantity, which was exactly u at Lagrangian trajectory plus Lx. So, let's don't worry about time. No? Divide by L. So where this R star is a Lagrangian trajectory. And what essentially he did, he defined the new field is as delta Lu divided by A delta Lu. So this is not exactly what we expect, because there is extra gradient this R star. So why at all we should go to the, why at all we where this Lagrangian trajectory comes into the play. So that's Lagrange trajectory is not. So if what for us in our formalism, what you can do is what you would do if you would take u of x is u by a of u, right? Or you can first rescale it by L and then do this, just like we did like before. So, but in any case, it will be something different. So certainly, it's different from what Simon did. So why is it done? So what is different? What is the important ingredient which make it different? I'm getting lost. Okay. And now we remember about Galilean transform. Why Galilean transform? Because you see, this is we started. What Simon showed is that we rescale differences, velocity differences, and velocity difference is a quantity which is invariant under the Galilean transform. So we take a quantities which are invariant under Galilean transform. So what it means that you quotient with respect to Galilean symmetry. So when you take quantities which are invariant with respect to Galilean transform, it's the quantities which label equivalence classes with respect to Galilean symmetry. So let's do this explicitly. So idea. Yeah, there's no Galilean symmetry for shell model. No. Well, there is a way to put it in, but not in a way that. So idea, not in the shell model we consider. So idea is a quotient with respect to Galilean group. So AG is a group of Galilean transformations. So we have group of Galilean transformation, and let's try to make a quotient. There are two problems on the way. Problem one, which is easy. Problem one is has to do with the fact that Galilean transforms are not statistical symmetries. Remember, we said the statistical symmetry is a symmetry which maps invariant measures to invariant measures, and this was useful because it made this extension of definition, it made the time scaling statistical symmetry, but it doesn't make Galilean transform statistical symmetry. So this can be yes. Well, I want to become a statistical symmetry as a quotient, but in fact, with the matter of fact, I will not succeed if it was not. No, you see, I want. No, it's not that. I want to remove this. I have to quotient this symmetry out. But before I quotient this symmetry out, I want to make it symmetry at least. I want to make it because otherwise this transformation doesn't have sense, because it takes my measure and after the mapping by this operator, measure is not anymore invariant. So I'm losing invariance, and I cannot do anything else. So because all our we are working with symmetries, statistical symmetries. So every operator we do, it should map invariant measure to invariant measure. It does not, so it's not good. So what does this mean? It means that even if mu is invariant, it doesn't follow that SGV mu is invariant. So we cannot apply these operators to measures because we lose invariance. So solution is simple. A solution is assume something which we always assume in turbulence, so space homogeneity. So restrict our study to homogeneous measures. Which means that assume that any space translations applied to our measure doesn't change the measure.
But then it could not be probability measure.
Why? Okay, good point. So it's very nice. Well, I was by purpose hiding one of the moments. So here, in order to do this, you need to you assume that mu is a periodic measure. How is it? No. It's a no. It can be probability measure. What's the problem?
Because it has positive.
There's no problem. It's okay.
No. If you have a region, yes, where it is non-zero measure, and then your translation doesn't intersect with it.
No. It's you see. As a matter of fact, this is abstract so far. But in principle, so assume the following: assume that this is a measure on a space of vector fields, and consider the vector field, which is, for example, consider periodic vector fields.
No. If you consider on a torus.
On a torus, yeah. But now open the torus to the full space, so that it become a full space measure, but just periodic. And then now you say that my measure doesn't change if I shift. Yeah. So actually.
That's very huge restriction.
That's a strong restriction, but it's also a restriction that usually in theoretical turbulence people do.
Sorry, it wasn't a torus. It'll be like.
It's not a torus. It's on.
Periodicity is 2 pi, and here you're asking for all r.
Yeah, does not.
After this, it's possible because if you have 2 pi periodic, you shift it, it's still 2 pi periodic. And then kind of it becomes, it could be a complex set.
Yeah.
Yes, because like you consider shift on epsilon, that's a different field, but if you shift on 2 pi, it's the same field. So it's
Yeah.
not contradictory.
There is no contradiction. So the field should be. It can be. Yeah.
You cannot use this argument that you
Periodicity refers to the field. The measure is supported on periodic vector fields, and the measure is time translation invariant, not the field. Okay. So this can be solved. So you just say that your measures are all homogeneous, and then you can then SGV is a statistical symmetry. So this you can check just by direct calculation. So this is the first problem. So the second problem is a hard one. We're close to the very end. The second problem is hard. And this problem has to do with that HG is not normal. same trouble. It's not normal subgroup, but it's not normal in a different way. Right? So remember what is the commutation relation? If you take first Galilean transform and then flow, it's the same as first taking flow, then the same Galilean transform, and then shift. And then you have to put a shift, space shift on a distance at which the origin traveled. So what we do, we just do the same procedure. So we define equivalence class. Yeah. And try to see what happens with equivalence classes. So we still can quotient the space. So quotient the space is not a problem. It means that you for each point you define equivalence class, and then the set of equivalence classes is a quotient space. Problem is a causal quotient group, because because HG is not a normal subgroup, we cannot quotient group. No. I will have to do different thing. You will come up with the R star. So that R star will come up. So let's just draw. So this is our equivalence class. So we have a point, x, and we have a trajectory. It comes to some point ct of x. So now now take another point. It doesn't come here, never. Where it goes to some other place. And to come from here to there, you should make this shift. Actually, you should make this shift. So this is ct x prime, and these two are linked by the translation. So what you can see that in order to in order to associate different points of the same on the same equivalence class, together with moving them, we always have to shift them so they always stay on the same line. So how you do? Essentially, you do the same business. You define representative set, which gives one point everywhere. And then there is certain amount of derivations. I will try to make it understandable. So first of all, idea is that even though every 2 points always escape from the same equivalence class, but you can make a clever adjustment always by shifting by the shift, so you keep them on the same equivalence class. So you have to together with the flow, you always have to shift a little bit. In such a way they stay in the equivalence class, and then you define the flow below. And then you have a chance to define the flow on the...
Here, the problem is that you have here both S and G, two elements,
Yeah. It's bad.
But is it unique vertical line on which you are?
Well, it's not a line. It's three-dimensional space.
Yeah, I understand. Yes.
Yeah.
It's not. It's infinite dimension.
No, it's HG is three-dimensional group.
Yeah, but okay. In any way, you have there two things, V and T, two parameters.
Well. The equivalence class is three-dimensional.
Yes, equivalence class is three-dimensional.
Yeah, but now what it tells that if you take any 2 points, they will be on different equivalence class, but we know where. We know how to shift exactly so well, no, this is not the right picture. Sorry. This is not the right picture. This is like this. Yeah. So you by the shift you go to the same equivalence class, not the same point equivalence class. So you by extra shift you can recover equivalence. Well, I'm not telling you that you should understand how to recover equivalence from a picture. I will write a formula. It's a bit.
But it's unique.
Yeah.
The point is unique. Yes.
So how you recover? So first of all, let's recall the definition. So Z is a subspace of X, is a representative set. Set if for any point of X there is unique Galilean velocity depending on X, such that the Galilean transform projected on Z. And this should be measurable. Okay, so it's the same definition, but now instead of time scaling, we have Galilean invariance. Okay, we also define projector as we did before. Projector. So exactly what this transformation does, it moves from X to Z, and so Z equal Q of X is exactly this, is G of X of X. Let's taking point, you go down. So now every small time dt, you should make this shift v dt. So let's do it. So every time change dt, we add a shift dr dt. That's exactly v dt, right? Because we shift it, 2 points split it, we add we put them back. But what it is, this is a just dynamical system, right? Because X is trajectory, this is velocity vector, so this is a equation for particle, for trajectory in the physical space. So we define shift trajectory, which just satisfies this equation. So we call it RT, depends on initial point, such that, so it should satisfy this equation, d RT dt equal, and this is, so what is this we will call, no, I will just write it here. dt it equal this. Where so where the intuition comes is what is this? This is something which is first you move to the time, but then remember we always shift origin. So we shifted the origin and then we computed velocity. I mean, it's not completely intuitive, but this is what it is. Next step, definition. So now you see, now at moment you give me function v, right? At the moment you given v and x, this is function of, this is just velocity field in space and time. If you fix x and fix v, this is just velocity field. So we can just tell that vx t is incompressible. It's called incompressible if gradient is computed with respect to r, right? Vx rt is 0 for all this is just definition. So you choose v, and then it's a vector field. If its gradient with respect to r, divergence with respect to r is 0, we call it incompressible. It's just if by chance if this happens. But that's a very important message because the next theorem tells you that it has two parts. First part is that is definition of the flow. So first is that indeed we can define a flow on Z. So it's motion, shift, projection. And shift is exactly with respect to this trajectory. So if you do these three pieces, you always move, always shift and project. You are doing well on Z. No? So you really can you can project dynamics on Z. And the second part is here there is if Vx is incompressible, then zeta equal projection of the measure is invariant for omega t. That's very important. So I have a flow, and I'm telling that if I just project measure, it will be invariant for that new flow. But it only happens if V is incompressible. So that's a sufficient condition, but it's generally it's necessary. So it tells you that if you are lucky to define your function v, so this function has zero gradient or zero divergence, then you not only can define project dynamics, but also you can project a measure. And this measure is invariant. Everything is
I'm sorry, but am I correct that when we define this projection of flow, the time moment 0 is kind of need to be chosen?
Yeah, time moment 0 need to be chosen. Yeah.
Choose another one, we will get another flow.
No. Flow. No, it will. No. This is time. This autonomous flow. No, it's not. Yeah, normal flow. There is no need for. What is? But initial time it defines every. You see, at every time and every point, define trajectory, and with this trajectory you define the flow. So it's kind of.
Because t is present.
T is.
And if you shift, it has 0 as a special.
Well, that's not real, but you prove its flow.
No, the fact that it's flow, that's okay. Yes, we prove it, but would it
Which means it doesn't matter what initial time you take automatically.
No, but I don't see why during the projection you didn't use the 0. So if you can write it at the same, but say write not R0 equal to 0, but say R10 is equal to 0.
Well.
Then you will get in the end.
No. That if you do, this is consistency condition. This is consistency condition exactly that because at t0 you should be at z, and in order for t0 you should be at z, this should be 0. Yeah, because you have two conditions for the flow. One is that flow t1 times flow t2 is flow t1 plus t2, and the next is that flow at 0 should be identity. So this is just to justify that flow at time 0 is identity. So it's so this is one theorem, and another. No, you don't know. So far, you don't know. I mean that if V gives me incompressible flow, I'm good. Yeah, probably you cannot, but we will see that you can.
So it's probably you cannot, but you can.
But, well, for Navier-Stokes you can, or for Euler. For Euler you can, but in general you don't know. Well, certainly if you take all of this, for example, applies to Burger's equation, and you cannot. Yeah. And that's why this whole theory does not apply to Burger's. But for incompressible Euler, it has, because for incompressible Euler, this incompressibility will coincide with physical incompressibility. We'll see it just in a second. So just second theorem, which I will not even formulate, I just say it in words. So under proper conditions, on V, which essentially is symmetry conditions. The projector the projector Q commutes with scaling space and time scalings. So this one more line of conditions that I don't want to put, but if you put even more conditional V, then V commutes with a projection. V commutes with a projection. It's what does mean is that you can just you can define essentially what it means that it means that you can define scaling operators for the new flow. So if V is good, you not only go down to the Z, you have the dynamics here, but also you have scaling, you have all the symmetries inside. Yeah? So you kind of project your dynamics on Z, and now you can live in Z, because in Z you have symmetries, the ones that you need, times space scaling. You have flow, you have invariant measure. So you can forget that you was in space X and you're now in Z. And at the moment you are in Z with symmetries, you can quotient time scaling, as we did before. Because you are here now, and you have all ingredients which were needed for the quotient of the time scaling. You have all the scalings, all the commutations. So you can do, so somehow you do this double quotient. First you quotient Galilean transform, and then you quotient time scaling. Okay, so the last point is to understand what it means. What it means. Take Euler. Remember that our points in Euler are fields. And we need to take velocity. Take origin. Yeah, that's a good function. So it maps field to vector. So what it satisfies. Okay. Now first let's check incompressibility. What's this? So what is V? V is this stuff. Vx RT is V R space Phi t of x. So x is this is our initial field, right? This is URT. Let's put this. No. Just a second. Yeah. So that's oh, sorry. This is good. So this is U T. And this just puts R to 0. So this is so incompressibility for Vx is incompressibility for this field. So we're good. So we're good in the sense that all this, despite its kind of looking that in general this is these requirements are special, but for Euler they are all satisfied. And incompressibility condition that we obtain, which is demanded by the actually group structure, it coincides with the physical incompressibility for our original system. There is one conjecture which probably not so probably not so complicated, but I didn't prove it. So is that this v of x, which is a unique possible choice. So there is strong indication that actually you cannot satisfy all the requirements by any other well, up to no, u of 0, because one of the requirements is that should be a scale invariant. If you put it at certain point, which is 0 is the only scale invariant point. For example, what you need is that if you rescale x, this will be just rescaled version of the vector. And with the rescale, I strongly believe this is true, but I don't have a proof. Anyway, this certainly works for this choice. And well, no, we're talking. Well, this is. You see, this is kinematical. This worked for Euler, for Navier-Stokes doesn't matter. What is not? What does not? The difference of Euler Navier-Stokes is only on the invariance of measure level. So as Simon tells that these transformations, they work whatever system actually is. The only moment that we remember it was Navier-Stokes or Euler is when we say measure is invariant.
There is for this Gaussian transform, we work for Navier-Stokes as well.
Yeah. Mm-hmm. So this is so now, as we say that it works. So now let's write what is exactly this flow. So now we can write a flow which is where it is. Yeah, this flow. So now let's derive what the flow is. So first we need to solve this system. And we know that this is just our flow, our velocity field. So RT is exactly our Lagrangian trajectory. Okay, so after we have Lagrangian trajectory, so now let's compute this stuff. First, let's see what is a projector. What's a projector? Projector is by definition Galilean transform at x. This is our field, and this is subtracting 0. Right? Remember, so this is field, this is u0, and Galilean transform means just subtracting this value. Simple. So now let us see what happens at z at time. So this is kind of time 0. So what happens at time t? It will be omega t z. We rewrite this formula. We now know that this is our trajectory, the Lagrangian trajectory. That. And what it is? So that we call u of x. Then we evolve it. So this becomes, so this becomes, let's see, u of r. No? This becomes u of rt. This moves r star inside, so this is u r star plus r t. And this put r to 0. Oh, no. Well. So this is what? This is a Gaussian transform of. This is Gaussian transform of the whole business. So this is. So you subtract from this field its value at 0. So let's call this just x. No? So and this is all exactly what Simon did, only missing just space rescaling, which you can also add. So this is exactly what Simon did, and this transformation. So what it does? Physically. Physically, you just take your particle, and then you take a reference frame and move it with a particle. And this gives you this new field moving, which you see. You see it on the. It's like when you see the flow swimming. So your motion just follows the flow, and you see what happens around you. So this is exactly what this field means. So that's field is known has a name. So this is called quasi-Lagrangian formulation for the fluid dynamics, and this goes to, I think it goes to 80s. So it's this Belinicher-Lvov. So essentially, that Lvov was putting forward. So physicists know this for a long time. So the difference is that we understand now the quasi-Lagrangian formulation. It comes from the quotient of the flow with respect to Gaussian transform. So it's actually not. It's not a physical construction, it's rather algebraic construction. And another thing which is important is that we understand that it only makes sense for incompressible flow. If it's not incompressible, you won't get any useful information, because you will not be able to carry the invariant measure. Yeah. So don't even try. Okay, I think that we should finalize. Well, I write few conclusions that we had. Just to finalize this part. Conclusions. So first is we understand what means fusion of symmetries. Fusion of symmetries that we saw explicitly done for Euler or for shell model it can be understood as as two quotients. Quotient of space, of phase space, and quotient of symmetry group. Yeah? And that's non-trivial, because this is non-trivial because not normal. So actually, we say that fusion means that we need to make a quotient of symmetry group. You cannot do quotient of symmetry group because the subgroup with respect to which you do quotient is not normal. You cannot do, but for these exactly particular cases, one is time scaling symmetry, another is Galilean scaling symmetry, you can make a trick and do quotient, do something which has just right properties of quotient that we need. Just for these two subgroups, because of the specific commutation relations that we have. The second part through this fusion you get statistical hidden symmetry. Which is weaker. So what means weaker? So now you essentially understand why the symmetry that you get on the quotient space can be restored if all the previous are broken. This is what Sergei told exactly, that you in a projection you can have, for example, a loop when above it's something completely chaotic. So essentially the idea is that you have something which is completely asymmetric, but if you project it in the right way, it becomes symmetric. Because all this part which is breaking the symmetry is projected out. And it turns out that you don't need to project out a lot, because you're in infinite dimensional space. All you projected in shell models just time symmetry, which is one dimension. And in Euler, we projected time scaling and Galileans, which is four dimensions out of infinitely many. So it's not so costly. So this is second thing. Another interesting thing is that intermittency in this picture comes from hidden symmetry, which in turn comes from commutation relations. So the intermittency, specifically the power law scalings, you can follow back to the commutation relations. And the final part which we saw is that the necessity to quotient Galilean invariance requires homogeneity and incompressibility. And this is quite fun because these two conditions come from commutation relations. But they are satisfied in Euler by physical reasons. So it's kind of coincidence between algebraic requirement and physical property. So I think that what we do now, we can just make a little break. Then essentially we finish with the course, and what we can do is we can briefly discuss kind of perspectives. Or so who is interested can stay, who is not. But there is, we can still take the fruits and drinks. So let's take a 5 minutes break and then finish. So let's talk about some, let's say, perspective. So what we want to understand, what we want to do, and in which direction we want to work. So first of all, what exactly the hidden symmetry statement? So there are two sides. One is that there is this symmetry. The hidden symmetry is a transformation that transforms invariant measure to invariant measure. And hidden symmetry conjecture is that it is restored. It means that whenever you apply, it's not just transformed to a different invariant measure. It doesn't change the measure. And from this, we can derive many things like intermittency and so on. So first of all is to verify if this conjecture is true or not in different physical systems. So verification of statistical hidden symmetry in physical models. So here what we do, it was say shell models, for example. This we can say yes, because what is done is that there are solvable models which is completely verifiable, and there are other shell models where you can verify it to a very large degree numerically. So for this we are confident. Now for the Navier-Stokes turbulence. That's very partially so far. So these results that Simon showed last time about multipliers, that essentially all is done, but there are essentially very interesting difficulties what you face on this way. So that means Navier-Stokes means that like for numerical analysis, numerically. And there are also experiments. And it's also partially in the same way because the universality of multipliers was verified for experimental data. So only Kolmogorov multipliers. Yeah. So that's that.
Experiments are like laboratory?
No, it's not. It's not laboratory. It's like laboratory. They take a hot wire and measure the atmospheric motion somewhere in the desert. I think this was a date. Because you need high Reynolds numbers. High Reynolds numbers is actually easier to get in natural environment when there's
Desert.
in desert. Yeah. Just put it very high. Measure. Okay. Another thing which is interesting is analysis of a rescaled system. So we have a rescaled system. It's essentially the same system as Euler, but with extra projection. But very little we know about it. For example, what about conservation law? Certainly, the rescaling breaks all the conservation law, but probably they you can still kind of look at it. It will be interesting. Okay. Another point is other group aspects. Other group aspects. For example, rotation. The rotation was completely ignored in our analysis, but there is a strong evidence that, for example, that scaling laws for longitudinal and transverse velocity fluctuations have different scaling, and this kind of I can cite my recent conversation with Greg. This kind of hints toward that it may be related to rotation or different representation of rotational groups. So probably there is something which we can take from rotation in this construction that make it more complicated.
But why can't you do what you did here with rotation? What would be the problem? If you do Galilean and rotation?
Well, rotation is you see, rotation is it's a complex. Essentially, what both Galilean and time scaling, they were not compact groups. Rotation is compact group, and somehow this makes a difference. So it's not clear. It's not clear what you gain so far. So how to make the same thing, this procedure, but in a way that you can really get something extra non-trivial. So it's, I mean that, right? Why don't you do? That's exactly the issue. So why don't you do? But do it in such a way that something comes out.
If you just put it directly, it's gonna.
No, directly doesn't work. Other systems or groups. For example, transport. So transport equation, the ideal transport equation is this, right? So you have extra symmetry. Extra, so scalar scaling symmetry, which just moves theta to any theta, for any c. Right? So multiply by constant, it's symmetry. So you can and then here you indeed just do exactly the same procedure. Your quotient with respect to symmetry. This quotient is very easy because this symmetry commutes with everything. So you just do usual quotient. There is no problem with normality. You just do a quotient and that's it. No, U is a velocity velocity field, either self-similar velocity field or velocity field with a group of Euler. So U is that velocity field that we had before. So in one particular case we did it with Simon. So we expect to have preprint. So who is interested? Maybe next week or in 1-2 weeks it will appear. And here. There is interesting the connection with zero modes. So that there is a branch of turbulence research which relates intermittency to zero modes for that particular equation. Okay, so that's it. So next is better understanding of algebraic structures. So here you can do many questions. So what we did, we took two different subgroups. One was subgroup with respect to time scaling, another Galilean, and just used the specific commutation relations and showed that for this specific commutation relation, everything works. But everything is specific still. So, at the same time, it worked for both of them in different way. So maybe there is something more general and abstract behind it. So maybe there is some kind of quasi-quotient that you can do on this level, but probably, let's say, on a larger class of subgroups. And our subgroups is just example of this too. So maybe there is something which we don't see, which is more general. No? So we have two particular situations, group situations which work. Maybe this is not the only, there are more, or maybe they are part of something more general. Well, certainly interesting, more solvable models. And that's what I just said, that's what Andre is trying to do. So we have solvable models for intermittency, which has this hidden symmetry with respect to time scaling. But it's extremely hard and actually not clear how to do any either solvable model or just construct a field which will have both hidden symmetries, hidden scaling symmetries and hidden translation symmetries. The two symmetries that Simon told last time. So the statistics is invariant with respect to hidden scaling, and also invariant with respect to hidden translation. It means going from one trace of Lagrangian particle to another Lagrangian particle. That's not clear how to do. Certainly, it's interesting. The interesting question is rigidity. Rigidity and non-bifurcation. So let us assume that everything worked. You have measure, you have system, it's hidden scale invariant. Now, if you slightly perturb everything, will it still be preserved or not? So usually, this is the whole, in dynamical system is the whole area of this research. So you have a solution and symmetric. So why the symmetry is not broken if you shift slightly, or under which condition it will break? So it will be changed. And this is the second part, bifurcation. So and at which condition, for example, hidden symmetric measure becomes some different non-hidden symmetric measure. So what happens?
What are you perturbing?
Perturbing the flow.
How would you perturb the equation?
Equation, yeah, original equation, for example, original equation. And this is I mean, there is a lot of on level of shell models. You have a huge testing background. What you can do, many. Or you can perturb, for example, you can perturb the convection term, quadratic term. You can perturb keeping the symmetries intact. People do this. For example, you can do it in Fourier space. You can remove some of the Fourier interactions in self-similar way, and it kind of already not an Euler, but has all the symmetries and keeping the incompressibility, everything. So where the rigidity comes from? Why it's rigid? Rigidity of hidden symmetric. Will or not the invariant measure will still be hidden scale invariant and hidden translation invariant. Yeah. If it was in the beginning. And if it will, and how this change happens. So usually in bifurcation theory, this change, for example, is associated to some eigenvalue, for example, passing the imaginary axis. No? Then you have Hopf bifurcation. No?
Do you have any numerical example?
There is one example which looks to be, it's a bit hard, but there is no very clear numerical example. But there are some examples which kind of, it looks like it's possible to find the numerical example for this. Well, and the final part is the part that we actually wanted to discuss, but certainly no time, is dissipation. I'll just tell you what happens. Dissipation. Or viscosity. So when you take Euler, rescaling gives you rescaled Euler, right? Or hidden Euler. That's not true for Navier-Stokes. Take Navier-Stokes. You get hidden Euler plus viscous term, but the viscous term cannot be expressed in rescaled variables. So essentially what you get for the viscous term is viscosity divided by scale and divided by amplitude. And the amplitude is, remember, amplitude is intermittent quantity. So essentially what happens that whenever you go to the rescaled variables with the dissipation, you get term which smaller the scale, stronger it fluctuates. So what happens is that, let's talk about the shell model. It would be easy. So what happens is that on a line of shells, so you remember that we have a forcing range here. It's at around 0, 1. Then we have inertial range, inertial interval here. So what happens that because this is intermittent, there is the dissipation range is also very wide. So there is a dissipation range which is roughly as wide as inertial. And what happens here is a mixture. So this intermittent dissipation. So it's a mixture of the inertial like dynamics and quench dynamics. And this happens in an intermittent way in a large range of scales. And certainly it's very interesting to understand this range because this will help a lot to interpret the data. Because with the data, numerical data is, you don't get very large range of scales, and in order to have a good data, you need to resolve this piece. So kind of half of the scales that you resolve, and most expensive ones, is not where you see properties of inertial range. So that's kind of, this is a big headache, and good to understand what happens. And one of the ways out is to use different and actually hidden symmetric dissipation mechanism. So that is possible. So you get something which is called extended hidden symmetry. So that's kind of artificial way when you, instead of viscous term, you put something different. It's still dissipative term. It removes energy, but it collapses all this interval to just 1 point. So you don't get the dissipative range is not growing as you increase Reynolds number. So that's though it's not physical, but it may help for the theoretical reasons, just to kind of separate the things. So that's also the ongoing things that would be interesting to do. Well, and if someone has other ideas, would be also very welcome. So. Well, other aspect of other aspect of turbulence is certainly, and actually it's quite a headache. Is what I told, like this rotation.
Well, can you say like spontaneous stochasticity and all that?
Well, spontaneous stochasticity is also an issue. It's probably related. So
how does it come into this picture?
you see, what happens is spontaneous stochasticity. So just recall, spontaneous stochasticity is a. So what's the difference between spontaneous stochasticity and hidden symmetry? So hidden symmetry is a study of symmetry of the invariant measure. So you take time goes to infinity. So you take a long time and you average. So it's about a stationary state or statistically stationary state. Spontaneous stochasticity is about solving Cauchy problem. You give initial condition, you want to solve, you don't know what is the solution time 1. And it turned out that in the limit in the inviscid limit, solution remains to be stochastic, even though there is no formally stochastic terms in the equations. So the relation is that even though you are at finite time in the spontaneous stochastic solution, but at small scale, it already recovers hidden symmetry. So it's small. It's kind of this small scales. They work like a boundary condition, and so at small scales, hidden symmetry is already recovered. So it's not recovered. When here it's recovered in the universal range, for the spontaneous statistics, it's recovered, but somewhere deeper for small scale. So there is also a range where this hidden symmetry is recovered, and this, I think, should affect the whole convergences and all these universalities of the spontaneous stochastic solution. So I believe there is a connection, but that's certainly not something which we even. Well, we know that this happens. By the way, now there is a paper coming out of Dim Abandak, who was a visiting student for 2022. Yeah, so and he in particular directly showed was one of the things he observed that there is a recovery of the hidden symmetry at small scales, even at finite times. So there is a connection, but developing of this connection is certainly interesting.
But there's at the formal level, it's also calls for the development of what you did today, but at the random level as well. Add some layer of.
Yeah, certainly. Yeah, certainly because yeah.
You need to solve a problem to select a factor.
Yeah. So it means that spontaneous statistics imply that one of the formulations of the flow operator is not a map. Is a flow. It's actually because probably the correct definition of the inviscid limit of the Cauchy problem in the inviscid limit is a stochastic process. So it's not a flow map. It's a flow kernel. So there's extra complications that comes from what we see observationally. So that's also interesting.
Invariant measures would give you some additional information if the measure would be ergodic.
Well, ergodic we certainly ergodic we always assume. Well, it's not that we assume here. We not in today's lecture, but in all applications we assume ergodicity because it connects measurement to theory. But because all the measurements is from time averaging. And theory is based usually on analysis of measure. In order to match them, you need ergodistic hypothesis. I mean that time averaging equal the measure averaging. Yeah. So from practical point of view, but now from theoretical point of view, well, the problem is that for in these limits, we don't always understand how to formulate this, even the formulation sometimes, even to formulate this property sometimes is difficult in the limit.
No, because it's possible to consider the measure is ergodic average, but not only by the time, but by the group. Yes, and in that case, you automatically get certain symmetries of group. Yes, and can it be helpful?
Can you say it again?
So you can consider not just time action,
Not only time,
but
okay.
group action, and consider
This group action.
averages of the groups.
I see. So I see.
Then you automatically get not only the things preserved under the time, but also certain properties of the group. It definitely works for abelian, yes?
Mm-hmm.
Should give you something for non-abelian, but I don't know what is that.
Well, that is an interesting thing too. Yeah. That's kind of in the spirit of a random merging group, right? You go from times, instead of evolving time, you evolve some other group.
No, this is related to rigidity, because this is the factor, because in that case, definition of your measure is kind of doesn't depend on what it doesn't see the difference between time and other symmetries. And in that case, kind of, it's easier to work with rigidity.
Okay, so thank you. We talk about it. So we're 5 minutes even after the threshold. So thank you very much. So let's thank all the auditorium who had this patience.
Yeah.